Okay, now lecture note is uploaded. So last time we introduced D-brain, a couple correction. So yeah. So analogy of electromagnetism. So the Maxwell equation is something like a J, and then so Maxwell equation. So let's see. Is the d star f is equal to J, and the f is equal to 0. So this is usual Maxwell equation. But if you assume there is a magnetic monopole, you can define as the electric current and magnetic current, so that the QE is the integral of star f, and then Q magnetic charge can be understood as the integral of F2, like this way. And then, as you know, they satisfy Dirac quantization condition. So this is Dirac quantization condition. Yeah, in the presence. So if there is a monopole. The similar thing happens in the D-brain. You can define the so last time I didn't include the QP CP plus 1. So this is the DP brain. How the DP brain couple the Ramon. So this is Ramon P plus 1 form. And then here D-brain charges is called D-brain charges. So you have to include this D-brain charges. And then so DP brain so DP brain is the electric source which has the and also D minus P minus 2 brain is the magnetic source, and then DP minus 4 brain. D minus P minus 4 brain is the okay. So maybe let's assume D is equal to 10. So this is 6 minus P brain. 6 minus P brain is magnetic source, and this will create indeed so this will create it's coupled to CP plus 1, and whose field strength is GP plus 2. Field strength is, so this is Ramon. It's coupled to, and they couple. And also this one is coupled to, let's see. So you take Hodgdale G is Hodgdale of G P plus 2, which is the, if it is 10 dimension, 8 minus P, 8 minus p. So therefore, it's coupled to 7 plus p. Ramon. Okay. So this can be understood as the DCT 7 plus. This is everything consistent. That's what's going to happen. Here p is assumed less than 4. Less than 4. Yep.
I think the Maxwell equation, the first one, you have a force star on the right side.
You mean this one?
No. Yeah.
This is the Maxwell equation, right?
You should have a.
Oh, Hodge, sorry. You're right. Thank you very much. Then my lecture note may have mistake. Okay, thank you very much. That's true. Okay, so then, yeah, that's true. Okay. So then, indeed, QP is measured by as follows. Yeah. So the QP is measured by indeed G tilde 8 minus P, and then S, 8 minus P, and then Q6 minus P is measured in a similar way in upstairs, and S P plus 2 is defined by G P plus 2, and then they are obey indeed Dirac quantization condition. This is what I missed last time. So they obey the Dirac quantization condition. And we will explicitly write down the different charges later. Different charges can be just computed. If, for instance, D brane, if you have D brane and D brane, and then so you can have open string wrapping around, or closed string just moving from one D brane to the other brane, and one can compute. One can compute D brane charges explicitly, but we will do it later, and we will explicitly confirm this Dirac's quantization will be satisfied. That's what we are going to see in the later chapter, later lecture. Okay. So this is the last time part I missed. Okay, so today we are going to talk about the teleology. So teleology is the very important it's very important. So first, so it's a duality with string theory. Essentially, string theory on S1 with radius R, and then the same string theory, another string theory on S1 1 over R. Well, maybe more precisely speaking, you have to include alpha prime correction. What's the alpha prime? Alpha prime over R. So this is the So that's a called teleology. Moreover, so one can just do the toroidal compactation. You can just do the number of so this is circle compactation. It's called circle compactation. Or more generally, you just do the which is the Banach product of circle, the copy of circle. So this is called one can put on string theory. And this is called toroidal complication. And this triangle complication is very important to learn so-called later, also in T-duality, and also later we will see so triangle complication appear also T-duality will exhibit T-duality, and also it's used by hydraulic string. Hydraulic string theory. Yeah. So so this one we explicit. So this is left hand side is left moving is bosonic. Movers, and then a super string. Right mover. And for right mover, you need a triangle complication. Okay. So to and then also this T-duality enrich. So T-duality enrich D-plane. T-duality will give rise. Also, actually, it will give rise to D-plane. In particular, so last time, so we introduced 2A and 2B by picking a different way of the GSO projection. So last time, so the Ramon sector GSO is 1 plus minus 1 to the F over 2. So that's the GSO projection operator for Ramon sector. And then this will pick 8S or 8S or 8 conjugate spinner. Okay. So either plus or minus, you pick either spinner or conjugate spinner. That's then type 2 and type 2B will be determined which projection operator you will pick, plus or minus. Okay. So that's the how we obtain the two types of string theory. In particular, so 2A is the 2A is the opposite chiral, 8S vector plus 8 spinner in left, whereas the 8C. So this is 2A, but 2B is the opposite. So it's the same chirality. So you pick the same chirality for type 2B. So let's see, this is opposite chirality. Opposite chirality. And then this is same chirality. So depending on same chirality, depending on GSO projection operator you will pick. It depends on which GSO projection operator you pick. Okay, so that's and then they are indeed related by, if you put on a circle, they are the same theory, but a different radius. Same theory indeed. It's a very magical property, and this same theory is called it's called the T-duality. This is related by T-duality. Okay, so the circle complication is very important if you indeed consider the superstring, because they will give rise to some duality between two different strings. That's what we are going to see. Okay. Today's lectures, the 8. Okay. So yeah, so this the picking which spinor representation is really coming from GSF projection Raman sector. So that's into I didn't explain very well last time. So that's the result of GSF projection. Here the eraser is not that good quality. Yeah, from now the lecture is going to be really interesting. It's going to be beyond the 2D CFD and also beyond the like a lot of duality and so on. It's really super string, non-perturbative dynamics and so on. So before going to superstring, let's consider bosonic string. So let's first consider S1 compactation of bosonic string. Okay. So bosonic string, as I mentioned, on. So therefore we just consider on bosonic string on R 1,24 times S1. Okay. Then we just split. So we will do the same thing as before. So x mu of z is equal to. So this is the model expansion for bosonic. We have a model expansion for the holomorphic sector, and then anti-holomorphic sector is the same. And then we identify the p mu as the 1 over yeah. So let's see. So we do this same as before, which is x mu of c plus x bar mu of c bar, and then this has the center of mass coordinate and r4 prime over 2, and you have 0 mode, and then another 0 mode t, and plus alpha prime over 2. So indeed, what I'm doing is really repetition, but it's going to be important. So if you look at the 0 mode and plus oscillator. That's what's going to be. So 0 mode becomes important once you do introduce this the circle complication. For instance, so the other direction. So if mu runs from 0 to 24, everything as before, the same as before. For instance, if mu is 0 to 24, for 0 mu is equal to for both mu 0 is just a momentum over 2 p mu. So therefore it's going to vanish. Okay, sigma it's going to vanish. Okay, so that this direction has a periodicity by like this way. If mu runs for before, okay. So they cancel each other, okay. They cancel each other. On the other hand, so mu is equal to 25. It's going to be very interesting. So, for instance, the momentum is quantized. Okay. So if its mu is 25. So let's consider this one is the x25 direction. The string can lap like twice, okay, like this way. And also, it has the momentum has to be quantized. Okay, so it has to be quantized if you compactify. So this momentum has to be momentum p has to be quantized because it should have periodicity. So therefore, indeed, so momentum so this is called. So P has to be quantized. P has to be quantized. P25 has to be, so if it is radius R, so momentum has to be quantized in the unit of 1 over R. So N is integer. Okay. So this is called Kawasaki line momenta. And also, how many times the string wraps is called winding number. So once imposed, let's see, sigma goes to sigma 2 pi, you can wrap the so once imposed, sigma goes to sigma plus 2 pi, x of 25 of sigma can be changed to the roughly speaking, sigma plus 2 pi is equal to x25 plus 2 pi r times w. Okay, this is called winding number. So you have periodicity if you have periodicity. So w is called winding number. Winding number. So you can wrap the string w times. And then, so therefore, if you include this, if you include this condition, then it turns out that the x25 direction, the zero mode has to obey the following. I don't like this. It becomes really dirty. It's not eraser. So if you impose this condition and look at the compare with this one, so then it turns out that the alpha 0 25 plus alpha 0 25 bar, this momenta has to be 2n over r alpha prime over 2. Okay. And then alpha bar 25 0 minus alpha 0 25 is indeed, you get this one. W. So that's how you obtain so you get from imposing this condition. And if you plug this one into here, this one here, you will see this condition satisfied, and the momenta is indeed n over r. So therefore, another way to see that this one alpha 0, 25 is indeed equal to n over r minus wr over alpha prime. So this is just, you can just solve this simple equation. So then now so let's look at the mass spectrum. So now a mass spectra is given by, so if you consider the if you just do the circle compactification, this mass can be understood. So the string really, if it is wrapped, let's see, yeah, if you string wraps on S1, so that everything becomes, it becomes point particle on the R124 direction. So the mass is of the string is indeed given by only 24 direction. It comes from 0 to 24. The momentum is really coming from. So you can just ignore they call it the Klein momentum here. You can just ignore the causal momentum here. And this is indeed equal to 2 over alpha prime, alpha 0.25 square, and plus numbering operator. So remember, numbering operator is indeed equal to alpha n, alpha minus n, minus n and n, and then sum over n, and mu, alpha dot. Sum over do we have this times n? Do you remember? Let me check my lecture note. So numbering operator, in the beginning, I just define, where was it? I think it's better to check if it is correct formula or not. Yeah, I'm correct. Okay, good. Yeah. Okay, good. So this, so once impose the, so this, so greater than 0. It is greater than 0, right? Yeah, greater than 0. Good. Okay. So this is the, you can just have the numbering of, so p mu is indeed given by here. And this is also the same if you look at homomorphic sector. So you have a level matching condition similar to the level matching condition alpha prime and n bar. So if you plug that solution into here and you just compare between them, so level matching condition will modify. So last time n has to be equal to n bar, but now without circle compactification, so what we obtain in the once you plug this one into here and just do the honest computation, so we'll get the n times w. So this is the level matching condition is modified by S1. So last time, so there's no winding number and moment, Klein momentum. So this, if there's no circle conjugate, this is 0. That was the level matching condition. And now we have this Moreover, m square is given by Crosstalk momenta, and then w square over r square alpha prime square plus 2 over alpha prime n plus n bar plus 2. So here I just sum them up and divided by 2. So mass is also depends on Crosstalk momenta, and then so this is modification. By circle configuration. Okay. And as you can easily see from here, this is very like suggestive. So n and w. So if you look at this one, so this level matching condition n and bar, and also mass. So n and w plays a very similar role. Okay, you can if you swap n and w in nice way, and this condition and this condition is invariant. The way you do that, if you do the n and w is exchanged, r is exchanged by alpha prime of r. If you do such a exchange, you don't change this condition, and also mass. So this is a simple observation. It's called teleology. So that's the so the Crosstalk momenta and the winding number is exchanged. The radius is exchanged. So here somehow this suggests that if you just start with the big radius r and try to shrink the circle S1. So if you compactify the string theory on the circle and the big radius and try to shrink the size, it's the same as the at self-radius r is equal to square root alpha prime. Something drastic happens. Once you try to compactify beyond the this is called self-radius, self-dual radius. Once you try to compactify beyond the self-dual radius, it's the same as just enlarging the circle. So you cannot shrink to the zero, essentially. The shrink to the zero means you just decompactify. So it's very magical property string theory has. That's called teleology. And teleology has more striking consequence. For instance, it will change some boundary condition on string. For instance, let's try to look at the how it behaves alpha 0 and alpha 0 bar by exchanging of this under teleology alpha 0 of 25. We'll get the negative sign, okay, as you can easily see. So if you swap n and w, you get the negative sign. Okay? On the other hand, alpha 0 bar stays the same. Alpha 0 bar stays the same. Okay? I mean, namely, so what I did is essentially you just exchange an n over r or n over r with wr over alpha prime. So then you can easily see by teleology, even though homomorphic sector, you get the minus sign, but the anti-homomorphic sector, you don't get anything. You just stay as it is, anti-homomorphic sector. Okay. So therefore, in teleology, the x mu, the bar, is going to be x mu of z. Homomorphic sector, you have a minus sign. On the other hand, sorry, in 25 direction, sorry, 25 direction. It's only, we are looking at 25 direction. Because the anti-homomorphic sector stays the same. Let's see. Okay. And this will be, so if you consider so-called open string, we will see. Anyway, so let's focus on first yeah. Okay. Let's first focus on cross string. So later, we will see that this will see the open string in open string. If you consider this the similar consideration, so the Dirichlet becomes Neumann and Neumann becomes Dirichlet. By boundary condition we modified by this transformation by TDR. So that's what we are going to see for open string. So that's what we are going to see. So therefore, if you look at it without Neumann is as I mentioned, there's no D brane, okay? But once you do the T duality, somehow magically D brane will show up. So okay, so let's look at this self-dual. What's going to happen? Something special happen in this self-dual radius. So this self-dual radius R is equal to square root alpha prime. Something special will happen. To see that, let's look at the metric. They call it the Klein convocation. So the metric of the convocation. So if you put the circle in whatever, you jump 25 times S1 with radius is equal to alpha prime. So this is so we'll consider Bosonic string with some manifold M25, and whose metric is given by as follows. So GMN dxn can be decomposed by causal current complication dx mu plus G25 25 plus a mu dx mu. So this is the Carter-Klein convocation. The metric can always written like this way. So as you can easily see, so this mu is related to so what I did, this mu is related to, of course, up to some shift by this one, the factor 25 mu. So it used to be here. It used to be here. So I just write down 20 metric is like this way. Okay, so this is GMN metrics, and I just decompose G mu mu and the G25 25. That's what I did. So this is the usual decomposition for Carter-Klein convocation. So of course this is 25 direction, and this is 25 direction. And I think, of course, you have to do some scaling by 25, 25 between G25 mu and a mu. But you understand roughly what I'm doing. Hopefully. So I think, precisely speaking, I think this should be 25, 25. Precisely speaking, 25, 25. I think that's what you need to do. Yeah. that's the decomposition. And then so under the coordinate transformation, 25 direction in under the so G mu nu. So if you do the this change of coordinate like this way, so mu, as you can easily see, mu is transformed as mu is transformed as d plus d lambda. Sorry, partial mu lambda. So you just plug in this one into here, you just get the extra piece. Okay? Extra piece. Mu plus partial mu lambda. So therefore, so you can just consider this mu, this direction, G25 mu or mu can be understood as the U1 gauge field. Okay. So indeed, so once you start with reaches 10th of 25 dimension, or 26 dimension, and once you just use this matrix, can be written as follows: 25 minus 2 times e to the minus sigma, and partial mu e sigma. I mean, you have to do the honest computation. F mu nu, where e to the sigma is equal to G25 and 25. So Einstein-Hirax action. So once you start with Einstein-Hirax action, you obtain the sum and the compact from S1. You will get the gauge field, U1 gauge field with scalar field. So this is usual way to do the Crosstalk comparison. So yeah, this is really literally what Crosstalk did. I don't know. I already forgot when they did the Crosstalk. And Einstein really likes it. And then let's look at that. If you have a field, massless, so these are massless fields, as you can easily see. So if you look at the massless field in string theory, so you have state operator correspondence, so you can just find a corresponding vertex operator. So corresponding vertex operator. So then, so G mu nu, GMN used to be, as I mentioned last time, a long time ago. The vertex operator is IKX. So that one corresponds to massless mode of GMN, the B and N. So, and the phi, dilaton. So, the metric, B field, and phi. So that was the state operator correspondence to tell us. And if you take mu nu as a, sorry, maybe I should use Mn, maybe, like this. So that was the case. But now we decompose the 25 direction and then 20, okay. 0 to 24 to 25. You have to distinguish. So therefore, you just do that mu nu, and here becomes mu nu, and B field also becomes B. So of course, mu nu is the symmetric part. Mu nu, B mu nu is anti-symmetric part, and so on. But you can just easily see 25. To the IKX corresponds to, and And also, you can just have another e to the ikx corresponds to mu and also be 25 mu. And also, if you just consider both 25 direction, you can easily see that this corresponds to sigma that appeared. So this one will tell you that you have. Well, I think bar. I missed bar. Sorry, bar. I missed bar. So left moving sector will give you a right moving sector 25th. Okay, left moving sector. So this is left moving or holomorphic. I don't know which one I call left and right, but holomorphic sector will give you U1 gauge field, and the anti-holomorphic sector will give you U1 gauge field. So therefore, what you end up with, so that corresponds to one gauge field and then another gauge field coming from B field. So the circle configuration will usually give you U1 left plus U1 right. U1 right, or holomorphic or anti-holomorphic, whichever. Gauge field. Okay, and now, so this is for at generic R, generic radius. But now let's look at this self-deal radius. So now let's look at this case, self-deal radius. And what's going to happen? Some special thing will happen. So let's put this R is equal to alpha prime over there, and then mass spectrum becomes as follows. So the mass spectrum 1 over alpha prime and square plus W square plus 2 and plus n bar minus 2. So this is the once you insert R square is equal to alpha, and this is the as you can easily see. Okay. And then now let's look at what's the mass spectrum. So what are the, so we just look at the mass spectrum over here for generic R, but for mass spectrum for self-deal radius will have something very special. So something special is, so the mass spectrum so I call it plus minus 1, and 1. Okay. Does it become massless? It should become massless. Why it doesn't? Oh, it does. Sorry. So if you plug that one into here, so 1 plus 2 times minus 1, right? So this counter minus 1. So this is equal to 0. Okay, it becomes massless. And another thing is the same, plus minus 1, 1, and 0. And also, you can do the same exercise for the other case. So plus minus 2, 0, 0, 0, 0. Plus minus 2, 0, 0. So the other case is just you have a 2 square plus 2 times minus 2. You get 0. Okay? C and D corresponds to again massless. Okay? C and D becomes massless. So there are how many? Oh, sorry. You should point me in. Okay, it should be minus plus. Do you understand what it means? Why it should be minus plus? Good. So you have a modified level matching condition n times w. Okay. So now for okay. I think what I did is like this. My table is like this. Good. So you have a modified level matching condition. You have a plus times plus. So you only pick the one sign. So upper sign or either upper sign or down, like how's that, down sign or whatever. But simultaneously, you have to pick the simultaneously the same one. So you have a n times w is plus 1. It should be n, capital N should be 1. And then if you pick the opposite sign, you should turn on the n bar, not like this one. Okay, so that is consistent with the modified level matching condition. And then you have the, so let's look at, so there the massless field has okay, so you have a new, so the upper massless field only satisfy this level matching condition, and it has to be equal to n bar. Okay, it used to be the level matching condition is always like this, right? So n and w are always 0. The previous the upstairs everything is the n and w are 0. But now new massless mode will show up, and then so you can just identify what kind of vertex operator one can assign this massless mode. So you have how many massless mode? 1, 2, 3, 4, 5, 6, 7, 8. So 8 additional massless mode. 8 additional massless mode. Okay. That's what you will get. So here, so 8 is suggested to 1 is 9, which is 3 times 3. That's what we are going to do. So 1 is previous massless mode, in the previous massless mode, but now we add additional 8 and you have a 9 massless mode, which is 3 times 3. That's what's going on. And we will see what it means from now. What it means. Okay, so then this is a good exercise to do to find what kind of vertex operator you get. This is homework. Indeed, today's this week's homework. I can give you only the A and B. So this A and B corresponds to the new vertex operator, which is the which only appear in a separate radius. So partial x mu a to d plus minus corresponds to literally this plus minus 2I x25 of c alpha prime and e to the I k x. And also this corresponds to A, and this corresponds to B. E to the plus minus 2I x bar 25 plus, just look at anti-homomorphic. Actually, this is square root alpha. Square root alpha prime e to the I k x. So now, in addition to this homomorphic derivative here, you can add some winding and the Cartesian momentum by just coming from this vertex operator, e to the some plus minus. Sorry, I think I told you. I think this combination, the combination will give you some certain linear combination. Yeah, so, and then if you look at if you define J plus minus of Z is J1 of Z plus minus I, J2 of Z, and J3 is what it used to be, is equal to e to the plus minus 2I x25 of Z over alpha prime, square root alpha prime, and this three direction is what it used to be, 25 of Z divided by alpha prime. That one is coming from really here. So the derivative, and this one new J plus minus will come from this extra vertex operator. And then this will satisfy the following OP. So this is a good exercise. So this will satisfy the following OP. So this is the new OP. So it used to be, it's a boring one. It used to be you have the x mu and z 25, 0 is what? So what kind of OP you would get? Well, what's this OP? What kind of OP do you get? So sorry, I think this is K equal to 1, so sorry. What kind of OP do you get? Do you remember? Or can you compute from now? Didn't you remember? 1 over z squared plus I think this one. Is it correct or not? This is not correct. I think just this one. Let me think. I think this should be the case. Yeah. So this will give you log c, right? Log c. Okay. And if you do the z derivative, and then essentially, okay, essentially this one, right? So therefore, this will give 1 over c minus w square, and then that, yeah, that's it, I think. Okay. It used to be a boring one. So if you don't include this exponential vertex operator, it used to be this is a really boring one. But now we have a new massless mode, and the new vertex operator. If you include new vertex operator, you will get the nice OPE. Tommy, can you close the door? And this one is called SU2 with level 1K. I'll find the current algebra. So for general K, so that's why I call it this is K. K is equal to 1. And if you do the mode expansion, this will give you, so as you can easily see, so the angular momentum, serial angular momentum, J plus minus is given by J1 plus minus I, J3, which is, as J2, sorry, J2 and J3. So they form the angular momentum, Ji, Jj, I, epsilon I, Jk, Jk. This is the usual SU2 algebra. So this is SU2 algebra, but now you have a current. So if you do the mode expansion, Ja of Z, which is sum over JAM, Zm plus 1, m runs for integer, and now we have the new current algebra, Ja n J B m is equal to epsilon ABC JC n plus m plus k over something, some number. I already forgot. I'm very not good at as you already noticed. We have a current algebra like this. And then to derive, so this JJ-OPE coming from really the OPE between the free bosons. So this XC, X0 is log Z. So if you use this OPE and just do the honest computation, you can derive this one. So this one is, so therefore, this strongly suggests that this used to be U1 cross U1 gauge boson. It gets enhanced the non-abelian gauge field. Okay. And SU2 cross SU2, you get SU2 cross SU2. So this will strongly suggest that the gauge field now becomes SU2 cross SU2, left and right. And that one is indeed will happen. And so the gauge enhancement, gauge field enhanced. At circle radius is equal to r. Now they can easily see, so this has this, what is the dimension of SU2? 3. 3 times 3 is 9. That's what I meant here. Okay. So let's see. So it's very special thing happened in the article the alpha prime, and on the other hand, if you move away from R self-dual radius, this SU2 cross SU2 is broken by Higgs mechanism. Okay, so that's what's going to happen. Okay, I think it's a bit early, but it's a good time to take a break. I think we're going to talk about the open strings. The consequent open string integral. Let's take a break. So did I post? Okay, it seems like people don't want to take a break. Oh. Did I post the homework already? I think I posted the homework already. Yeah, I think I made a mistake. I think I should put the M over 2 here. M over 2.
Maxwell State 直接就用在其实 Maxwell State 直接就用在 Spectra 上，就是我想象中应该是自动在Maxwell State
啊，是吗？Maxwell State 和那个不是分开的意思吧？就是它那个对就跟系数嘛。
如果它全都做在吉他上的话，那么所有都是Bosonic，没有合力。
为什么要挑？
不对，不对，不同 C 不是对应是那个 Fermion 和那个 Bosonic，就不同 C 特对应的那个 Bosonic
就是如果你全都直接做在Maxwell上的话，它 Maxwell State 全都是 Bosonic，因为吉他才区分出了Fermion。
就是哪里？
就是那个那叫什么 racing operator 不改变分域和分子，不能存在其他不对的条码，但它可以写直接存在其他，直接存在Maxwell上，它就应该是做到而且算的，它意思应该也是做到Maxwell，或者要么就是NS 得做到Maxwell上，然后RS 得最后在这个上面，但是算起来它的数目又不一样，它这是36个态，然后它这里基态就已经有8个，8种怎么乘出36个？所以不知道该怎么写，那是不是直接写？封皮都没拆，怎么干？我开始直接写来，它都在这上面，那就是72再乘24，他妈有点硬，所以不知道该怎么写，随便写就写。
这个4就是88吗？
就8×8。
他不做那个，就是不做直积分解式吗？
做分解只是写成另外一种形式而已，还是数学还是64有什么区别？
不，这有问题啊。
它只是把矩阵拆成3个部分，它只是把8×8矩阵拆成3部分而已。
有些不有物理意义啊，我在想，就跟你之前做那个
可以给它物理意义啊，但是
这样我们作用
它没让你这么写，是没让你这么写。
我就应该不是这样的吧？
就两种写法没区别啊，有纯的区别。
我觉得是，因为它不是去把它。我当时想的。我还有冗余的自由度。它不是，它为什么要分解啊？它不单独直接8×8，就每个8×8的写出来，不是每一个项对应一个那个，它分解它干什么呀？
分解它为了找物理意义啊，但你没分解前，你就已经写出来了，有什么用处？你写出来就是写出来了，有什么用处？
对，它可能是那个，就可能对应那个就是多重态，它可能不能算哎。
没对应，它就是算出来就是这个思路。
我对8×8算出来
就是这个思路没去。
我想的比如说
去把8×8矩阵分成对称、不对称，还有那个就是 trace 的部分，没区别。只是写法不同。
对，这个选这种方式什么意思？它到底选这个还是每次就是他做合同炸药还是
这个是能看懂的。
啊，对，这我能看懂。
这个他连NS都没说，那啥什么意思？
哇，打死
不中的，
我对56怎么来的？64也8吧。
这个应该是把4个塞分在一起呈现。它是把4个塞分在一起呈现。成长的就
应该是。
你就根本不用管这个，看这个就够了。
行吧。
但是 math 我是真的不知道该怎么写。全算在吉他上数是对的，然后不做在吉他和那个数就不会。
肯定做在吉他上面。
不是吉他，作用在 Y 看不上。不是作用在 master 上。
它在那个表示面是代表什么？就是那个 NS 和 RC， 还有指头。
就是不是 master 的那个，这还不是 master 吗？这是 master。
反正他是写阿尔法这个角色的。
这他写阿尔法给做在零上面。
啊？
你不说是真的吗？你在说锤子吗？
啊，不，我当时想的是那个，就他之后的时候区分那个，区分在那个不同的 C 上区分的。不是，这个他应该是对于。
你觉得会是36在乘上64？
我不知道，我
觉得有，
我现在还是不搞懂这个，就值得直接分解在做什么？就根据我这个对离代数表示的浅薄理解，它每一个那个波动态是不计数的，就是你每次做一个那个就是在那算不算就造成波动态？
可别把肮脏数学加起来。
不是，本身就是你多动态是就是它每个对于本真值是相同的。就这部分里面，就是它可能是1加2加3这样子。
我觉得
2和3这个是简并的，懂吧？每个简并的。我觉得他们对于同一模式了。
我应该是作业。 use the raising operator on the message or on the background. Will it be this way or massive operator on radical band.
But the NS, so the vacuum is GSO projected. So the master state coming from psi minus 1 so that's massless. So then pre-successive state acts on the gradation operator on this massless state on NS. So NS, I think you need to, so mass 0k in NS is GSR projected. This one is GSR projected. And the massless state comes from 0k. That's the first massless state. And you need to act on another creation operator to get the massive state, first excited state. Is it okay? Does it answer your question?
So it's the same for R state.
R state vacuum is indeed 8S or 8C. So depending on GSO projection. So then the vacuum is just a S plus and S1 S4. Right? This is, and depending on even sign of how to say upspin or odd sign of the odd number of upspin, you get the 8S, 8C. And you just act on some creation operator to get the first exercise. And you just count how many of them.
So this will be incorrect. It should be 8 plus 8, 28 and times the massive.
Yes. What's the correct answer? I already forgot, to be honest, massive. I think 128 bosons. So you can just act for NS. You just have -1 here can act on, and 1 side -1/2 mu. So I think this, and also you can act this one. Sorry. And they can act on this one, and also you have another one. I think these are first excited states you can get. And you just count how many of them. These are NS massive mode. And then R sector, you should get the same number of massive states. Same number of massive states from R sector. That's what you should get. Did you get that one? You haven't done it yet. Okay. So this is NS. Ramond is the same. Ramond, you should get same number of the first massive states. Essentially, you get this one, right? Alpha minus mu acts on it, and then psi minus 1 acts on it in the ground state. Ramond ground state. You just count how many of them in Ramond. Yeah. That's what you need to do. Yeah. And then you just count the NS and Ramond, and then also NS Ramond, NS. I mean, it's the same exercise, I think you need to do. Okay, shall we start? So let's get started. Let's see. Okay. So now, so in the previous exercise we did is indeed so alpha 0, 25 is by under TDRT you get the minus sign. Homomorphic sector of minus sign. On the other hand, on that homomorphic sector do not have anything. It stays as it is. And then x prime 25 ZZ bar means indeed you get the minus sign homomorphic sector. And then on that homomorphic sector is there as it is. That's the after TDRT. So this x25 it used to be like this way. So let's look at the consequence in open string. So open string. Let's look at the consequence of open string for this one. Indeed, so as you remember, z is equal to e to the minus iw, where w is equal to, I think as far as I remember, sigma plus it. So this is the coordinate transformation we use from cylindrical coordinate to the plane coordinate. Should be the case, right? Yeah, it. So this is what we have obtained. If you use this relation in open string, so the consequence of this one is the changing of boundary condition. So indeed, sigma x25 of ZZ bar or ZZ bar. So this is Neumann ratio. Which one? Acting on 0 and pi. So is it Neumann ratio? Which one? Do you understand? So you have the sigma direction and 0, 0 and the pi, right? 0 and the pi. The sigma equal to 0 is what? Means like this way? do you understand? Always sigma derivative 0. Do you understand what I mean? or like this way. So it's always the how to say, there has to how to say, it ends on the 0 and sigma by normal direction. So it just oscillate. So therefore this one is called what? Which boundary condition it is? Neumann. Good. This is Neumann. Under this transformation, you can just check that the this one is mapped to the following. Ratio t x25 x prime 25 z bar is equal to 0. So therefore, this becomes the ratio. This becomes the ratio. That you can easily see from mode expansion we looked at before. After normalization, what was the normalization? So let's see. So it used to be x25 is equal to some x20. So 0 mode, center mass mode plus x bar 25 plus minus I squared alpha prime over 2 alpha mu minus alpha, so 25 t plus alpha prime over 2 alpha 0 mu minus alpha 0 mu and sigma. Okay, that used to be the case, plus oscillator. And if you swap alpha 0 to minus alpha 0 and alpha 0 to alpha 0, this becomes alpha 0 25 plus alpha bar 25 0, and this one becomes minus alpha prime over 2. So alpha 0, this should be 25 plus alpha bar 0 25 of sigma. So the role of sigma and t are swapped, okay, up to sign. Okay. So as you can easily see from that transformation. So therefore, the boundary conditions of the sigma equal to 0, derivative of sigma equal to 0 is swapped to derivative of t becomes 0. And of course, derivative of t equals 0 means you have to fix, any time you have to fix a position on sigma. Okay? You have to fix whatever. You can vibrate whatever in the, but at the boundary 0 and pi, the position is fixed. That's what it means. Okay? T derivative, so always the position is fixed. So therefore, you get derision. Okay. So then, the derision is Neumann's. So now here, Neumann. So you can have, you can vibrate. So whatever. So 0 and pi. And if you have vibrating mode, okay, so I think ground states are like this way maybe, and the first excited states are like this way, and next excited states are something like that. I mean, it's just ordinary quantum mechanics. You just start with this one and go back and then come back. My hand drawing is horrible. Like this one. Okay, this is second excited state. It will give you the momentum. Okay, of the open string. That's right? The quantum mechanics. That will give you. So this is n equal to 0, n equal to 1, and the purple is n equal to 2, and so on. N equal to 2, and so on. Okay. In other words, you essentially have a cos of sigma pi and n times sigma, something like this. Okay, so that's a wave function, and n is a momentum. So the n is a Crosstalk line momentum. Okay, so now, let's see what's Crosstalk line momentum will be encoded in Dirichlet under the TDRT. So x prime 25 at the point pi, x prime 25 at point 0 is equal to 0 and pi d sigma x prime 25. Okay. And as we know, the sigma and t, the role of sigma t is swapped on the TDRT. Therefore, this becomes 0 pi in the odd variable. So here you have a prime. Okay, so the after TDRT, but it's before TDRT because there's no prime here and t here. And we know if you do derivative with respect to sorry, I think I should put t here. N times t. Yeah, I think t plus minus sigma. I think that's what's going to happen. T plus minus sigma. Then, if you take derivative with respect to t, you get the momentum. This is momentum. So this is momentum. So therefore, you get the 2 pi alpha prime and p25. This is just momentum. And this is equal to, indeed, 2 pi alpha prime. Momentum is n over r. Okay. And we know that the r is related to alpha prime r, okay, which is, I call it r prime. Therefore, this is equal to 2 pi n is nu r. So therefore, this means what it means is as follows. So what it means is that you start with some circle compactation of string, and you have a vibrating string, open string, vibrating open string, and you have Crosstalk line momentum. Okay, Crosstalk line momentum or momentum has to be quantized along 25 direction. So this is x25 direction, and the radius r. So now, the radius is becomes r prime, which is alpha prime over r, and then so it's now here is Neumann boundary condition. So you can freely vibrate by Neumann boundary condition. But now after TDRT, so this is TDRT. So it has to be fixed position. It has to be fixed position. And then momentum is the open string momentum is just a is mapped to the just a winding number, like this way. So this is n equal to 1, where n equal to 2. I mean, it becomes like this way. Okay, like this way. This is the first excited states. The second excited states is mapped to like this way, and of course, ground states are like this way. Ground states are like this. You just the division. You have a division, and you have an open string winding around. So this is n equal to 2, n equal to 0. And here you have a moment that just corrects the prime moment along the 25 direction. Okay, so that's the interpretation of the open string. So if you do the TDRT, naturally, so D brain show up. So this is indeed D brain. Yeah. And then let's look at a bit more detail about this TDRT in open string. For instance, if you we know that the we know the open string can generate the gauge field. Let's suppose the how this Champerion factor and also D brain is associated to Champerion factor. Last time I introduced Champerion factor. So how it ends, and then let's look at how they are related. Okay. So this one is you have a bunch of D brain, and you can just have the Champerion factor where it ends. Okay, where it ends from I and J, and the gauge field is just coming from the numbering of where it ends. So they must be related. And to see that from this analysis, we just turn on some holonomy or with some loop. So let's suppose you have U and a gauge group. U and a gauge group is broken to U1 to the N by turning on the Wilson loop along X25. Okay. So which means that the gauge field has some expectation value in the it's UN gauge field diagonal matrix, then n by n matrix, but we just consider this has something diagonal 0, 0, and then up to some normalization 2 pi r. So this suppose x25 has such an expectation value. Okay. So just constant, some theta 1. That will break the UN gauge field to U1 to the N. So that's commute this diagonal element. So therefore, in locally, so this x25 can be written so this x25 can be written lambda, partial lambda, 25 minus I, so that the lambda is indeed just a diagonal matrix e to the I x25, theta 1, 2 pi r, and e to the minus x25, I times 25, theta n, 2 pi r. Okay, so that's the locally it look like this way. Okay. And as you can see, so this will give you the momentum shift. So I mean, here you, I mean e to the x, so I times, sorry, I think I missed I. So as you know, so if you have the gauge, if you turn on gauge field, partial mu is mapped to partial mu plus I and mu, right? I and mu. So therefore, P mu is shifted by P mu plus I and mu. And as you can easily see from here, so this is just a momentum translation. So therefore, open string momenta is shifted by this amount. If you turn on gauge field on 25 direction, shifted by e to the I theta 1 dot e to the minus I theta n. So that's the diagonal matrix. And we know from here analysis that the Cartesian momentum is mapped to the winding number. So therefore, this shift can be easily encoded to the position of the D-brane. So if you have Champeton degrees of freedom I and J, is corresponds to the phase between them. So therefore, e to the I theta. It's a very heuristic argument, but this one is employed by Brochinsky. Is momentum shifted, so therefore momentum shifted by 2 pi n plus theta j minus theta I divided by 2 pi I. And so therefore this will give you this is after T duality, so momentum P25 is written like this way, and after T duality, so the relation between 25 over pi minus x prime, 25, 0, you have the same 2 pi n plus theta j minus theta I, and then r prime. So therefore, this means that the if you turn a holonomy or Wilson loop, what you end up with is that the indeed. So this will end up with just putting a different position on the D-brane. D-brane different position, theta I, r prime, theta j, r prime. Okay, theta j, r prime, like this way. And then, of course, this after r prime. And then the open string will just so Champeton degrees of freedom and theta ij is just the open string between them, or some other direction. So now, as you can easily see, so the difference between them, so this is n equal to 0, this is n equal to -1, n equal to -1, and maybe you can have something like this way. So this is n equal to 1, n equal to 1. Sorry, this color choke is not good. Like this way. So that's the condition. So once you turn on the Wilson loop or gauge field along the 25 direction, you can have different position of D-brane. And that will give you Champeton factor, which D-brane it ends on. The phase, the relative phase between them of the Wilson loop will give you the position of the D-brane. And of course, we can just compute the mass spectrum of this open string. So mass spectrum open string. So mass spectrum open string is given by like this way. As we saw, this is alpha prime n minus 1. So was it like this way, right? Yeah. Okay, so this is open. So this is open string, like mass. So the difference between cross string is, as I mentioned, so this one is used to be, I think, it used to be something like this one, 25 over square plus 4 times alpha prime n minus 1. So this is cross string. And then, as you guys did in the exercise, so this factor of 4 really come from whether you have a sigma is equal to 0 to 2 pi, or sigma here is 0 to pi. This factor of 2 gives rise to factor of 4 here. So that's you did in an exercise. Okay, so let's forget about this cross string spectrum. So then let's look at the here. Just plug into here. You will get as follows. This one will give you 2 pi n plus theta j plus theta I divided by 2 pi alpha prime prime. Strictly speaking, this, I think this is, yeah, I think this should be okay, yeah. So square plus 1 over alpha prime and minus 1. And as you can easily see, to get the minimum mass, you have to set n equal to 0. N equal to 0, and then let's look at n equal to 0, so this becomes theta j minus theta I over 2 pi alpha prime r prime, and the square plus the excitation mode. So therefore, the mass should be proportional to the length between them. Okay, and times string tension. 1 over 2 pi r alpha is string tension. Therefore, the mass of open string between this minimum mass is really the proportional to the length of the string between them. Okay. So this is really the Higgs mechanism you get. So what it really does here is all the, so UN goes to U1 is literally what we are doing is that if you have a bunch of D brane and stack of D brane, so n copy of D brane is indeed by turning on this Wilson loop, it becomes this gives us UN. So by turning on Wilson loop, and if you look at the theta picture, so it becomes a bunch of n D branes, theta 1, theta 2, and theta 3, and theta 4, and so on. And that will give you the only U1 to the n square. That's a Higgs mechanism I told you last time, and then so U1 really come from the open string ends on its side, okay, like this way. But by Higgs mechanism, you get a mass between the open string between different D plane. That is proportional. The mass is proportional to the length of the string. And yeah, of course, different U1 will come from different open string ending on the itself. So that's a picture by turning on Wilson loop. A TDR picture of turning on Wilson loop. Okay. So then, I just write down the corresponding vertex operator. So in U1 to the n, so the corresponding vertex operator is indeed given by 0k and I direction, and this is massless, and alpha 25 minus 1 k, 0k. I is the corresponding vertex operator is partial p x mu e to the I kx. The corresponding vertex operator is the x25 e to the I kx. And then TDR picture, this is equal to sigma x prime 25 e to the I kx prime. This is the corresponding massless state. So in order to have a massless, J has to be equal to I. J has to be equal to I, and n is equal to 1. That's exactly what happened. And this is the gauge field along the spatial direction. This is 25, coming from 25th direction, compact direction. Okay, so now it's okay. So more generally, if you do the okay, maybe getting maybe a bit fast, but anyway. Yeah. So let's look at the relation. So this is all bosonic strings. Let's look at the superstring. Okay, TDRT in superstring. In superstring. So in TDRT and superstring, especially, so this TDRT relates the 2A and 2B by TDRT. And of course, a superstring TDRT on S1, or more majority or TD. So as I mentioned, so this TDRT transform as a parity transformation x9 of z, and then z bar is transformed. So now instead of 25th direction, I just put the 9th direction. So maybe I should be a bit more specific. As first, let's consider R1,8 times S1, and this is ninth direction, X ninth direction. And then the similar phenomenon happen in the TDRT, TDL, X prime ninth direction have a minus sign. In summary, sorry, holomorphic sector. Holomorphic sector should have a minus sign. Holomorphic sector should minus sign, and the supercompound invariance, but since it has a supersymmetry, the super part of X is psi. So psi 9, Z also has the minus direction. So this is, in other words, it's called parity transformation. Okay, so this is the parity transformation. You just put the minus sign in one of the directions. That's called parity transformation. And we know that type 2A and type 2B are parity transformation. So in other words, the swapping 8S and 8B, 8SC, so it's parity transformation indeed. Okay, so therefore, and moreover, so we can just see that so we just define the creation annihilation operator on the Raman Fermi is the indeed we just define how do you define plus minus I as far as remember some number times psi 0 I plus minus psi 0 I plus 1. That's how I define. Let's take a look at my lecture. I didn't print out that part. How did I define previously? In the raising and lowering operator? I already forgot how I define. Oh, 2i. Sorry. 2i. Yeah, 2i plus 1, and then 1 over square root. This is how I define Raman creation annihilation operator. I runs for 1, 2, 4. Okay. And in particular, if you look at the ninth direction, so if you look at the gamma plus minus 4, then this becomes square root 2 psi 8 0 plus minus. Oh, did I put the I here? Oh yeah, I here. I here psi 9 0, right? So therefore, if you look at zero mode of this ninth direction under TDRT, you get that this creation annihilation operator is swapped, okay, by ninth direction. So therefore, under TDRT, it becomes gamma minus plus minus creation annihilation operator is swapped. So therefore, this will give you the some different parity transfer. End up with parity transfer. 8S and 8C will be modified. So it just changed the relative chirality between C and S and C. Okay. Yeah. So in other words, this will change this result in the, maybe I should write down here. So in the previous case, the Dirac equation involves S0 equation to plus, and S1, S2, S3, S4. Under the TDRT, it becomes S0 equal to plus, S1, S2, S3 becomes minus S4. If it is upspin, it becomes low. Downspin, if it is downspin, it becomes upspin. on the t-duality. So therefore, 8c, sorry, 8s corresponds to even number of up spin or down spin. How do I define? Plus or minus? I don't remember which one it is. How did I define odd number of minus 1? Minus 1/2, and hs is odd number of minus 1/2. Okay, that's how I define hs and hc. So therefore, they are swapped on the t-duality. So this end up with the type 2a is swapped to type 2b. Type 2a is swapped to type 2b. So as I mentioned, yeah, holomorphic sector. Yeah. It's, I mean, so remember 2a is holomorphic sector is 8b plus 8c plus 8b plus 8c, sorry. Okay. This is anti-holomorphic sector. And this is equivalent to, if you do the t-duality, it becomes, you just change only holomorphic sector. Holomorphic sector. So therefore 8b plus 8c plus 8b plus 8c. And then this, they have the same chirality. So therefore this is 2b. I call it 2b prime indeed. It's a parity, redefinition of the, but anyway, so essentially, if it has same chirality, it becomes 2b. I mean, it's S or C. The choice of S, C doesn't matter so much. Okay, so that's what's going to happen. So and then, so this is, and we are doing the same similar stuff as before. Then. So we know that the type 2a, you have a type 2 strings, you have a Ramon field p plus 1 form, and then G p plus 2 is a few strengths. It's just a derivative of this one. And 2a, p has to be even or odd. Which one? Even or odd? 2p's what? 2a even or odd? Either even. Which one? Okay, let's say where the D3 brain lives, 2a or 2b? Last time I told you, D3 brain. 2b. So therefore p has to be odd here. So D3 brain will give rise to ADS-CFT. ADS-CFT is coming from 2b. And this is even. Okay. And then so this Ramon G flux Gp plus 2 has the corresponding so this is 2a and 2b this is also in today's exercise, this week's exercise. So you can associate some space-time vertex operator. So where gamma, I will explain what it is. This week's exercise, this is really, you should do that. I mean homework, I try to give you nice homework to try so that you can understand the subject. So psi and gamma 11, this plus minus is chiarity. Is plus minus under this gamma 11. So gamma 11 you know, right? So this week I give you the chiarity operator last week. And then so gamma bar plus minus is given by this dagger of psi minus gamma 0. So this is the definition of bar. And then gamma mu 1 dot of mu p plus 2 is just an anti-symmetric product of gamma matrix. Gamma p plus 2 and then so it's just an anti-symmetric combination of the gamma matrix. So that this is the really anti-symmetric form, p plus 2 form, and then L and R is left or right movers. Okay. L or right are this one is the left or right movers. Left or right mover of the string. And it turns out that if you define like this vertex operator corresponding to the G flux, you can easily see P has to be even P in 2A, P has to be odd depending on the sign I pick here. Depending on chiarity I pick here. And you can do, so this is this week's homework. So you can just show by just using transformation of using a gamma metric and so on, you can show P has to be even on the 2A and 2B. And now, what are the consequences of T duality? How do you define T duality on this one? How they transform the T duality. So in T duality, so we will correspondingly have the right moving sector of the ferment. This alpha is plus minus. Plus minus is transformed beta 9, I call it beta 9, psi plus natural amount of Z, I mean the holomorphic. And then psi left moving. Oh my goodness. Why am I doing such a stupid thing? Sorry, my conventional R and left are different. I think this should be L. Sorry, it's a typo. It should be L, and this should be R. Am I correct? Which one is correct? Let's look at the holomorphic is right? I already forgot. Holomorphic right moving and anti-holomorphic left moving, as far as I remember. Sorry. What is it let's take a look at today's homework. Which one did I define? Okay. Okay. But I don't remember which one I call it right moving. Which one is first the right moving is holomorphic and left moving is the anti-holomorphic. So I think this one is correct, but that one is wrong. Right moving is this one, and left moving is this one. Anti-homomorphic. Anti-homomorphic stays the same. So let's change now. I will change your homework. So I think left is anti-homomorphic as far as I remember. And homomorphic is right as far as I remember. Okay? Okay. I will, if I'm wrong, I will correct later. Anyway, it depends on which one I call it right moving, homomorphic or anti-homomorphic. I don't remember. So as I mentioned, it's only holomorphic sector is affected. So as I mentioned, holomorphic sector you get a minus sign. Anti-homomorphic sector stay as it is. Okay. So then, and where beta 9 is equal to gamma 9 and gamma 11. That's the parity transformation 9. No, this is parity transformation. Of on spinner. So therefore, if mu1 to mu p plus 2 contain 9, 9 will cancel with this gamma 9. Okay, gamma 9. So therefore, in other words, it's transformed. If you have a c mu equal to 9, it's transformed under t derivative becomes c. It's cancelled. Or like if you have a c mu and a c mu 9 and so on, it becomes c mu 9 and c mu nu. 9 direction would disappear, but if there is no 9 direction here, it creates under 9 direction. Okay? It creates a 9 direction. Sorry, I should write a 9 direction. And also c mu nu lambda 3 form doesn't have a 9 direction. We get the c mu nu lambda 9. Okay. Do you understand which side is 2a and which side is 2b? So this is clearly p plus 1 is odd, right? So this cp plus 1 is odd. Left hand side is cp plus 1 odd. P plus 1 is odd means p is even. Okay? So therefore, left hand side is 2a and right hand side 2b. Okay? 2b. So therefore, this means that the c mu is indeed a couple to d0 brane. Okay? Couple to d0 brane. So this becomes d0 becomes d0 along the ninth direction becomes d minus 1 brane. Okay? Here d0 becomes here d2 d1 brane. Okay? d1 brane. d0 and this d associated d2 brane is becomes d1 brane if there's 9 direction. Okay. And this associated to d2 becomes d3 brane if there is no 9th direction. Okay. If there is no 9th direction. So this is consistent with what we have seen before. So for instance, if you have D1 brane, so here, so if you D1 brane on 2A and 2B, it becomes, so this is 9th direction. becomes D2 brane, and this is the D1 brane into 2B and 2A. Okay, under T duality. Okay. So this one, I'm just looking at this part and this part. Okay. So it's in general, it becomes a DP brane, either becomes a DP brane, becomes either DP plus 1 or DP minus 1, depending on this P direction spans for 9 or not. Okay? So that's how they behave under T duality. In the type 2A and type 2B. So that's what's going to happen. If you have circle complication, depending on, so this is when P is not included 9 direction, when P does not include 9th direction. This P does not include 9th direction. Sorry, the other one. Sorry. It increase the spatial direction like this way. I mean, if it has 9th direction, it becomes decrease, and dp becomes dp minus 1, and so on. Okay, and so on. For instance, if you start with type 2B configuration, whatever, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then, for instance, whatever configuration you can consider, but for instance, I just consider the following configuration, which appear often in string theory, especially how it's working on this kind of stuff. Now, my student is working on this kind of stuff. We can consider the following type of the configuration for the brane. So type 2B has the P is odd, but it can also have a NS5 brane. Okay? And for instance, if you do the you can just consider such a configuration. So then, for instance, you can just have the 3D theory living on, for instance, D3 brane, 2 plus 1 dimensional theory sitting on here. For instance, you will get some supersymmetric field theory, for instance. So for living D3 brane living on here is some kind of supersymmetric field theory. That will give you 3n equals 4 theory and so on. So then let's do the TDL along this direction first. Along this direction, NS5 brane is intact along the T duality, but D3 brane, since it extends to the x2 direction, it gets rid of the direction and becomes D2 and D4 in type 2A. Type 2A. And for instance, next one can do the T transformation, T-dual transformation of 9th direction. And then since it extends to the the ninth d2 brane extend ninth direction, it becomes how to say? It becomes point on the ninth direction after the t duality, and then again d4 brane extend to ninth direction becomes d5 brane, and this becomes d1 brane, becomes d1 brane, okay. And then it becomes again t type 2b. Type 2b. All this configuration becomes the dual configuration. And this D1, D5 configuration, especially, but NS5 brane is intact. Nothing will happen in NS5 brane. It's magnetic dual the fundamental strength. So fundamental strength, and also is coupled to B field. Okay? B field. So this is the NS sector. So what we are talking, everything talking about Raman sector. So NS5 sector is intact under the T duality. So that NS5 brane does not affect it. It's not affected by T duality. And then all those configurations are T duality, so they're equivalent. And if you forget about NS5 brane, D1, D5 will give you so-called instanton configuration. So D1, D5, for instance, if you do the one more T duality over here, you get D0 and D4. D0, D4. D4 brane. So this will give you the 5, so on D4 brane, if you forget about NS5, on D4 brane, you have 5-dimensional gauge field and then gauge theory, and there's some instanton configuration on the time direction. So therefore, so in spatial direction is R4, and somehow instanton will appear in some point here. It becomes instanton configuration. Yeah, and the number of D0 will give you K instanton. And that will give you so-called necklace of instanton partition function. This is the subject I'm working on. Okay, so therefore, as I mentioned, so this D brane will create the supersonic field theory, and also on. But this T duality will give you lots of duality between bunch of supersonic field theory. And in particular, as we will see later, this 2B will enjoy so-called S duality. We will see later. I just tell you a little bit. By S duality, it enjoy S duality. S duality swap NS5 and D5. And this D1 becomes a fundamental string F1. That we will see later. And this configuration also duality each other. Okay, so that's the T duality in superstring type 2A and type 2B. Any question? Okay, so today I went a bit fast, maybe. This is a place I plan to stop here. Now we are going to talk about the type 1 string theory. Okay, so let's briefly introduce type 1. Okay. Type 1. The reason why type 2 is type 2 is you have n equal 2. N equal 2. So 2A and 2B, why is it called 2? These two come from D equal to 10, N equal to 2, supergravity, coming from supersymmetry or supersymmetry. So these two come from, it's called N equal to 2. And we are now considering D equal to 10, N equal to 1, supersymmetry. We are going to think about. And it's 2 and 1, since it's reduced to 2 to 1, the number of supersymmetry will be reduced. It has 32 supercharges here, but now it becomes 16 supercharges. So that's a difference between n equal to 2 and n equal to 1. The reason why we would reduce the number of supersymmetry, we would introduce so-called oriented fold projection. So we would do the oriented fold projection. We reduce the number of supersymmetry from 32 to 16. So that's what we are going to do by introducing the so without D-brane, type 2 doesn't have an open string spectrum, but type 1 by introducing oriented fold, you will get the open string too. So let's briefly start talking about type 1, although we only have like 5 minutes left. So type 1, so type 2 string is the type 2 is the has cross string without D-brane. One cannot incorporate the open string. Okay, yeah. So this can be seen as follows. For instance, the last time I introduced the spectrum of type 2A spectrum, I didn't, yeah. So I didn't print out that one too. Let's see. What was that? Yeah. So if the so open string should be associated to 8B configuration. So this is the open string configuration. 8B literally means the alpha minus mu. One acts on the psi minus 1/2 in NS vacuum. So this is open string configuration as we saw the previous lectures. And if it has the n equal to 2 supersymmetry 10D, d equal to 10, n equal to 2 supersymmetry, will give you the either this will has the super partner 8s plus 8s, or it should have 8s plus 8c. It should have such a configuration. It should have two superpartners. And then, and unfortunately, the gauge field only have if the superpartner should have 8s or 8s plus 8s plus 8c. So it depends on 2a or 2c, the superpartnership. But as we will see, the gauge field should have only one superpartner. So that's I'm going to explain. Field should have one superpartner. So this is superpartner. Superpartner. So the type 2 string cannot incorporate the open string. So you have to break the supersymmetry n equal to 1. To have the open string, you have to break to the n equal to 1 in 10 dimension. And then two superpartner, you can see that from the spectrum of the previous lecture. I already forgot. Yeah. So for instance, dilaton has two superpartner. So for instance, in type 2 string, dilaton phi has the two superpartner plus minus, and that corresponds to 8s plus 8c, and also so graviton has the two superpartner and alpha, which is 56s plus 56c. So this is the dilatino, and this is the gravitino. They have two two copy. It appears that is a consequence of n equal to theory. But in 10 dimension, it's a spectrum. It's only one superpartner because of the number of supersymmetry. And that's what we are going to explain. What I'm going to explain, to break n equal to 1, 2 to n equal to 1, I will introduce oriented form, so-called. And then type 1 string is the 2b with orientiform plus orientiform projection. You get type 1. And it indeed has a D brane D1 and D5, and it also incorporates D9 brane. This is non-dynamical object, yeah, that's what we're going to learn next time. So let's stop here.